seconds, get ready to launch right. It'll launch right out. Launch right on. Okay, Scotty, you ready? I'm ready when you are, buddy. Okay, here we go with the countdown. 3, 2, 1, release.
Throughout the battle of the space race between the United States and Soviet Union, both unions experimented with remarkable and experimental technologies in the pursuit of the data and wisdom required to conquer this new frontier. The task of gathering this data itself was a tremendous challenge that required new aircraft capable of reaching the edge of space and pushing the boundaries of human understanding. One plane that stands out during the ascent of the space race was the X-15, a plane designed to be the first to break into the hypersonic regime and climb past the Kármán line, 100 kilometers above the Earth's surface, and break into space. The plane would help NASA develop the materials needed to survive the intense heat of re-entry, the structures needed to ensure stability and control in the hypersonic flight regime, and the development of control mechanisms for the vacuum of space, while providing the impetus to develop several new technologies required to allow humans to survive the vacuum of space, like the first of its kind, fully pressurized space suit. This was the world's first space plane. The plane laid the groundwork for both the Apollo program, the Space Shuttle, and the SR-71. To this day, the plane holds the record for the fastest ever crewed flight with a top speed of 6.7 Mach, leaving even the SR-71 in the dust as this rocket-powered plane powered through to the edge of space. This is the insane engineering of the X-15. When the X-15 was first proposed in the 1950s, no other aircraft came even close to its proposed capabilities in both max altitude and max speed. The closest any previous plane came was the X-2, which topped out at a max speed of Mach 3.2, less than half of the eventual record the X-15 would achieve. The X-15 wasn't a step forward in capabilities, it was a tremendous leap that would require the best minds in NASA, or the NACA as it was called then. The first step on this road to the record 6.7 Mach was developing an engine capable of powering such an aircraft, and for this, the designers had to turn to rocket propulsion. Even the advanced hybrid engines of the yet-to-be-developed SR-71 couldn't push into the hypersonic regime, and no air-breathing engine would be able to function at the altitudes the X-15 was targeting. The engineers knew the engine they required would need to produce around 240 kilonewtons of thrust at sea level with an ability to vary thrust output, while fitting into the narrow body of the plane. This powerful engine did not exist, and developing it would prove to be one of the greatest challenges facing the X-15. The first problem to solve was this variable thrust output, which was desired to give pilots more control over the aircraft and allow for testing at various speeds. Blasting straight into the hypersonic regime without extensive testing at lower speeds would have proved disastrous, as the difficulties of frictional heating were yet to be solved. Older engines like those of the Bell X-1, the first plane to break the sound barrier, achieved variable power output by simply selectively igniting 4 separate combustion chambers. This provided stepped power output, but not true throttle. The X-15 needed finer control than this, and needed to achieve it without adding significant weight and complexity to the engine. Added complexity would decrease the safety, putting any pilot in danger, while any added weight would significantly reduce the maximum altitude the plane could achieve. The X-15 achieved this control by varying the speed of its turbopump, which is the pump which forces the oxidizer and fuel from their respective storage tanks into the combustion chamber. Pumping fluid at the rate a rocket consumes it is actually a tremendously difficult challenge. The X-15 carried 8,165 kilograms of fuel and oxidizer, which the plane burned through in 85 seconds. That's 5,897 kilograms per minute. That task would require a powerful pump, and that pump would need a powerful energy source. Now, it may seem like an obvious choice to simply use a portion of that rocket fuel to power the pump, And indeed, this is how modern rockets like the SpaceX Merlin engine power their turbopumps. Turbopumps operate by spinning a turbine using hot, fast-flowing gas, but using the products of rocket fuel combustion in a spinning turbine would quickly lead to severely melted and broken turbines. The combustion products of rocket fuel are simply too hot for this application. The Merlin engine gets around this by using a very fuel-rich mixture for the turbopump pre-burner, which leads to incomplete combustion and lower exhaust temperatures. That exhaust has a large portion of useful fuel contained within it, but the sooty exhaust is not suitable for addition to the main thrust chamber, so that fuel is simply dumped overboard. You can see that fuel-rich sooty gas coming out of the exhaust here on the Merlin engine. The X-15 used an entirely separate fuel to power its turbopump. A monopropellant like hydrogen peroxide decomposes in an exothermic reaction when in the presence of a catalyst. In this case, hydrogen peroxide was passed through a silver screen catalyst, which caused the hydrogen peroxide to decompose into oxygen and superheated 737-degree steam. It was this superheated steam that drove the turbine, and the speed of the turbine could be controlled by simply adjusting the amount of hydrogen peroxide passing over the silver catalyst with the use of control valves. The exhaust of this system was then simply dumped overboard through this exhaust port. This was not the only use for hydrogen peroxide on the X-15. A similar system powered the auxiliary power system, or APU, which powered the plane's electronics. The pilot would also need some form of control when outside of Earth's atmosphere, where the plane's aerodynamic control surfaces would no longer work. So, the plane was fitted with thrusters on the wing tips and nose to provide control while in space. These thrusters were also powered by hydrogen peroxide. Using hydrogen peroxide to power the turbopump came with some challenges. This turbine operated two separate impellers, one for the liquid oxygen storage tank, which operated at 13,000 RPM, and one for the anhydrous ammonia tank, which operated at 20,790 RPM. These different pumping speeds ran on the same drive shaft, which necessitated gearing to achieve the appropriate fuel mixtures, but also incorporated serious safety concerns over accidental fuel leakage from the respective hydrogen peroxide, liquid oxygen, and anhydrous ammonia lines, as a spinning shaft is more difficult to ensure an adequate seal. Double seals were placed between each section in an effort to prevent mixing, while a system of pressurized helium purged the system. The choice of liquid oxygen and anhydrous ammonia was an interesting one. This engine needed to be powerful, extremely powerful, and getting it to the required thrust levels was going to need the right fuel and oxidizer combination. When speaking of rocket power capabilities, one of the first stops is specific impulse. Specific impulse describes how efficiently a fuel can convert its mass into thrust. To understand this, let's first look at the total impulse, which describes the thrust force generated over the entire burn period of the engine. We can graph this rather easily by plotting the thrust the engine is providing in each second of its flight. That may look something like this. The total impulse is found by finding the area under this graph, which gives us the total energy the rocket released. This is a useful metric in itself, but specific impulse is better because not all propellants are born equal. Two different fuel and oxidizer combinations could provide the same total impulse, but we need to consider the weight of the fuel and oxidizers themselves. After all, the initial weight of the rockets is always dominated by the weight of their own fuel. To find the average specific impulse, we divide the total impulse by the total propellant weight the rocket expelled. Going by this metric, a liquid hydrogen and liquid oxygen fuel mixture is by far the best. Hydrogen has the lowest molecular weight of any known substance, each hydrogen atom consisting of just one electron and one proton. The H2 molecules used in the liquid hydrogen fuel has a molecular weight of just 2, while RP1, the kerosene-derived fuel used for the SpaceX Merlin engine, has a molecular weight of 175. However, molecular weight is not the only factor in determining specific impulse. We also need to consider a multitude of other factors, like fuel mixture ratios, combustion temperatures, pressure ratios, and specific heat ratios. This is where a nice simple, specific impulse value gives us a clearer understanding of how much thrust per unit weight a fuel and oxidizer combination could potentially provide, without delving too much into the complicated physics and chemistry. And looking at this value, hydrogen is best at around 381 seconds at sea level, while the kerosene and oxygen combination of the Merlin engine has a specific impulse of about 289 seconds. However, it's once again not as simple as picking the highest specific impulse value, because hydrogen has a very low density, meaning we need a much larger volume tank. It's also a difficult fuel to handle, as it will boil off if allowed to rise above its extremely cold boiling point of minus 250 degrees Celsius, requiring insulation, boil-off valves, and last-minute refueling. To boot, this tiny molecule can seep out of the tiniest holes, even the gaps between larger molecules of seemingly solid metal. Despite its potential, hydrogen was not ready for this task, but would soon be put to use for the very first time with the Centaur upper stage after many years of development hiccups. There was a great deal of experimentation during this period to find a fuel and oxidizer mixture that would provide the specific impulse needed to get the plane to hypersonic speeds, and it wasn't just a matter of loading the most powerful fuel and oxidizer combinations into the fuel tanks. Increasing the specific impulse is directly linked to elevated combustion chamber temperatures, since fuels with higher impulses generally release more energy when ignited. This is one of the major hurdles engineers of this era had to contend with, as the materials and designs needed to survive these extreme temperatures simply did not exist. The traditional fuel of the time was a 75% alcohol, 25% water mixture with a liquid oxygen oxidizer, which has a specific impulse of about 269 seconds, not high enough. The water was added into this mix primarily to reduce the combustion chamber temperature, which of course reduced the impulse of the engine. To achieve that higher specific impulse, the engineers needed to figure out a way to allow the engine to survive the elevated temperatures that would come with a higher impulse fuel, and the only way to do that was by finding better materials or find a way of actively cooling the engine, ideally both. One way they achieved this was through regenerative cooling. Regenerative cooling uses one of the propellants, usually the fuel, as a cooling fluid. The fuel will be pumped through heat exchange piping that wrap around parts exposed to dangerous heat, like the injector nozzle, thrust chamber, and nozzle, where it can draw heat away from the metals it comes in contact with before being injected into the thrust chamber. This was not a new concept. The V2 rocket, which used that 75-25 alcohol mixture, also employed regenerative cooling, but the heat transfer rates were not terribly high. To be an effective cooling fluid, the fuel needs to have a high specific heat capacity, meaning it can absorb a lot of heat energy before its own temperature rises. Water has a high specific heat capacity of about 4,200 joules per kilogram Kelvin, meaning it takes 4,200 joules of heat energy to heat 1 kilogram of water by 1 Kelvin. We also want the fluid to have a high latent heat of vaporization, which means it takes a lot of energy to vaporize the fluid. We don't want the fluid turning into a gas in the cooling tubes. Here, water is strong again, boiling at 100 degrees Celsius, and that number will be even higher when pumped under pressure. So, now we are looking for a fuel that not only has a high specific impulse, but with great cooling properties too. Kerosene was considered with a slightly improved specific impulse of 289 over the traditional alcohol-water concoction, and was cheap and freely available at the time. However, when passed through cooling tubes, kerosene of this era had a nasty habit of forming clumps of impurities. This process is called polymerization or coking, and accelerated when exposed to the heat of the cooling tubes, which could clog the thin tubes and cause major problems. The RP1 grade kerosene fuel we use today was developed to combat this problem by removing the impurities from the fuel. Hydrazine, which has a specific impulse of about 303, was also considered, but it had a nasty habit of exploding when used in regenerative cooling, as its exothermic decomposition process can start at a temperature as low as 97 degrees, which can lead to a violent explosion. Eventually, the engineers, who may have been short a few fingers at this point, landed on anhydrous ammonia as their fuel. Ammonia is a fantastic cooling fluid with an extremely high heat capacity and high latent heat of vaporization, making it the ideal rocket fuel for regenerative cooling, with a higher specific impulse over its alcohol-water ancestors at 293 seconds. However, ammonia does come with its own issues. It's toxic and would attack many metals, like copper. The pressure gauges of the X-15, which contained copper, were consistently failing after 6 months of use, despite not being in direct contact with the fuel. This was annoying but deemed an acceptable trade-off for the fuel's benefits. This development process of the engine was fraught with difficulties and ran over both time and budget. Meanwhile, the airframe had to undergo parallel development without the final engine, instead using 2 XLR-11 engines which had previously powered the Bell X-1. These provided enough power to get the plane to 3.3 Mach and test some of the plane's flight performance characteristics, but fell well short of the requirements for hypersonic flight. In the meantime, data on the hypersonic flight characteristics of the X-15 were gathered using advanced hypersonic wind tunnels, but the engineers had no idea whether this data would be accurate. This was still a very new field of research. The design and requirements of a hypersonic aircraft that could possibly fly into space were so radically new and different that traditional aerodynamics textbooks had to be left at the door. This was going to require a completely fresh approach with all assumptions thrown out. For example, during the development of the X-15, a debate was raging in the NACA Ames research facility over the design of the nose for hypersonic aircraft like this. Julian Allen argued that any aircraft flying in this flight regime should be designed with a blunt body, something that completely contradicted the established thought of the era, which demanded for extremely pointed nose in an effort to reduce drag. Julian Allen argued that this blunt body design would create a bow shockwave, which would create a boundary layer of air around the vehicle and ensured the extreme frictional heat was kept away from the structure of the aircraft, and instead dissipated harmlessly into the atmosphere. The X-15 did incorporate these ideas into all of the plane's leading edges, including the nose and wings, and the idea would be applied to all re-entry vehicles in future. As the X-15 re-entered Earth's atmosphere, it would be taking a very high angle of attack approach to bleed off speed. At a 20-degree angle of attack, the upper vertical tail became completely useless, as it was severely shielded from the airflow by the body of the aircraft, whereas the lower tail would experience a marked increase in effectiveness as it dipped into the high-pressure zone caused by the compression side of the wing. So, this lower tail was essential for ensuring yaw stability at these high angle of attack re-entries. But this lower ventral tail was so large that it made landing on the plane's shorter skids impossible. So, the pilot had to jettison a section of it before landing, where it would deploy a parachute to land softly and hopefully undamaged. The shape of the X-15's vertical tail is one of the most distinctive features of the plane. The primitive-looking wedge profile looks like something someone may have designed with 300-year-old knowledge of fluid dynamics. Oddly, that's exactly what it was designed with. In 1687, Newton described an equation in his groundbreaking book, Principia, that predicted the force a flat plate in a moving fluid would experience. He imagined the air as a stream of particles that would strike the plate and transfer all of their momentum normal to the surface, and then travel parallel to the plate. He also assumed the particles did not interact with each other and there was no random motion. This, of course, is wrong. The complex fluid fields in this situation are much more complicated than Newton predicted, but bizarrely, his equation rather accurately approximates the forces on an aerodynamic surface in hypersonic flow. Let's look at the wedge tail surface as it increases its Mach number. At supersonic speeds, a shockwave will form at the point of the wing. This is called an oblique shock wave, and its angle becomes smaller as the Mach number increases. Until, at hypersonic speeds, the angle becomes so small that it almost matches the wedge angle. This looks oddly a lot like what Newton predicted for subsonic airflow, and indeed his equation becomes more and more accurate as the Mach number increases. And while the wedge shape begins to act predictably with this simple equation, normal thin curved aerofoils designed with subsonic fluid dynamics in mind begin to experience a dramatic loss of lift, rendering them essentially useless at hypersonic speeds. The wedge tail continues to perform and provide the stabilizing pressure needed to keep the plane flying straight. This does come with a trade-off of high drag, as the blunt end creates a narrow pressure zone behind it that drags the plane backwards. But this was of little concern for a short-range plane that needed to slow down quickly. In fact, the wedge tail was fitted with extendable speed brakes to even further this braking effect when coming back from its high-speed runs. Flying at hypersonic speed did not just come with strange aerodynamics. The heat of hypersonic speeds was one of the largest challenges that faced the X-15. A very specialized metal was needed for the task. The SR-71 utilized titanium, and it experienced a maximum temperature of about 300 degrees Celsius on its pointed nose and engine inlet spike during Mach 3 flight. This temperature was vastly lower than what the X-15 was expected to experience at Mach 6 and above. The effect of frictional heating does not scale linearly. It would not be dealing with 600 degrees, but upwards of 1000 degrees, far beyond what the titanium skin of the SR-71 could handle. Having to deal with the extreme external heat was difficult enough, but the designers also needed to contend with the extreme cold emanating from the internal cryogenic liquid oxygen fuel tanks. In images of the underside of the X-15, you can frequently see frost covering the belly of the plane, where the liquid oxygen tanks are located. There is only one metal on Earth up for this task: Inconel X. Inconel X is a nickel, chromium, iron, and niobium alloy that was capable of operating at lower temperatures while having extremely good heat resistance. Plotting tensile yield stress against operating temperature for aluminium, titanium, and stainless steel looks something like this. Now, if we plot Inconel X, we can see just how good it is at maintaining its strength at extremely high temperatures. However, Inconel is heavy. Designers estimated that an Inconel X airframe would weigh about 180% more than an equivalent airframe made from aluminium, and this was before the ablative materials were applied to allow for the highest speed runs. The ability to maintain its strength at elevated temperatures was beneficial, but there were plenty more problems to solve. Non-uniform heat distribution made accommodating thermal expansion and stress extremely difficult, and several redesigns of the plane's structure was needed to fix problems that cropped up along the way. During the plane's first Mach 6 flight, one of the quartz windows, quite worryingly, shattered mid-flight when the Inconel framing buckled due to thermal expansion. Thankfully, only the outer pane shattered and the pilot survived to tell the tale. The framing metals were promptly switched to titanium, which experiences lower thermal expansion, and the aft portion of the framing was removed entirely for a very interesting reason. The designers discovered during high-speed tests that the plane was experiencing extreme local heating in strange locations. One such hotspot was appearing behind the window, and it was the result of shock waves creating turbulent flow. These turbulent flows create areas of elevated heat transfer into the skin of the aircraft that create dangerous hotspots. To find and eliminate these hotspots, the designers employed a special kind of heat-sensitive paint that would change color when exposed to certain temperatures. After one high-speed flight, the plane returned with wedge-shaped patterns emanating from the leading edge expansion joints, which were small gaps in the leading edge to prevent buckling when the Inconel X expanded during flight. These gaps were creating this turbulent flow, and to fix it, engineers installed small strips of Inconel X over the expansion joints in an attempt to minimize the turbulent zones. They did get smaller, but were not eliminated completely. For the eventual world record-breaking flight, the Inconel X alone would not ensure survival of the plane. For this, the plane would need an ablative material, a sacrificial material designed to gradually burn and fall away from the aircraft, pulling the heat with it. One of the principal missions of the X-15 was to develop these materials. Multiple materials and application systems were tested throughout the X-15 program, and plenty of problems were found. Bonding the ablative materials to the surface of the metal proved difficult. Some simply fell off when the underlying metal expanded underneath it, and it could not stretch with it. These problems were found at slower Mach 5 flights, but if they appeared during the top speed attempt, the plane likely would have been lost. Another problem arose when the ablative material, after burning away from the nose of the plane, began attaching itself to the windows of the plane, making it extremely difficult for the pilot to see, which was a bit of a problem. The engineers looked at several solutions to the problem. One involved deliberately exploding the outer pane of the glass to remove the ablative stained portion. The engineers eventually landed on a less risky solution by installing a mechanical eyelid to the left window that remained closed until the high-speed portion of the flight concluded, ensuring the pilot had at least one window to look out of during landing. This was a relatively primitive solution and created some stability issues, as once open, the eyelid acted like a canard and caused the plane to slightly pitch up, roll right, and yaw right, an annoying but manageable problem. A slightly more terrifying problem cropped up with the final ablative material. This pink material, called MA35S, was sprayed onto the surface of the plane in various thicknesses, according to the local need. It worked well, but had one massive, glaring drawback. When mixed with liquid oxygen, the material would become explosive and could be triggered by a slight impact. A bit worrying considering the plane's oxidizer was liquid oxygen and spillage was not rare, especially as the plane had to be continually topped up from its B-52 dock as it ascended to altitude. The spray-on method could also potentially introduce the ablative material into the oxidizer lines too. To minimize this terrifying prospect, the plane was sprayed with a secondary white sealant coat to prevent the liquid oxygen from mixing with the ablative, and came with the added benefit, or disadvantage, of hiding the glorious pink colour. After a decade of development, on the 188th flight of the X-15, the plane was finally ready for its record-breaking flight. On October 3, 1967, William Knight climbed into the cockpit of the X-15, hanging from its perch underneath the wing of the behemoth B-52, which carried the plane up to 45,000 feet. Here, Knight dropped away and ignited the rocket engine, and with the help of two external fuel tanks, they roared for 2.5 minutes, pushing the plane to the yet-to-be-broken 6.7 Mach flight. In the attempt, the plane was destroyed. The ablative coating hadn't worked as well as hoped, and the plane landed with parts of the skin melted away. It would not fly again. The remaining two planes in the program flew just another 11 times in total before the program was shut down. Through the 199 flights of the X-15, NASA gained some of the most valuable data it has ever gathered. The X-15 not only broke speed records, but altitude records, when, on July 17, 1962, Robert White became the first man to fly a plane to space. The knowledge NASA gathered through this program advanced our understanding in rocket engine design, turbulent flow, localized heating, ablative materials, and hypersonic stability and control, all of which contributed to the design and development of the Mercury, Gemini, Apollo, and Space Shuttle programs, and provided Neil Armstrong with invaluable experience in controlling a rocket-powered spacecraft. Armstrong was a fascinating man, someone I knew very little about until I watched this documentary on CuriosityStream, an hour and 40-minute long documentary that had me captivated the whole way through. I was inspired by the story of a young boy who became fascinated by model aircraft at an early age and pursued that passion with every step of his life, becoming a licensed pilot at the age of 16, entering an aerospace engineering program at 17 through a military scholarship, before being drafted as an aviator into the Korean War, a stepping stone to his eventual career as an experienced test pilot and, of course, astronaut. A life of a man driven by a deep passion for aviation that led him to a life of greatness that will never be forgotten. This documentary alone is worth the astoundingly low price of subscription to CuriosityStream at $14.79 a year or $2.99 a month. But this is just one of many award-winning documentaries on CuriosityStream. And you will also get access to Nebula, the streaming service that's home to my Logistics of D-Day series, my new podcast Modulus, which launched another episode today, and ad-free versions of all of the videos you see on this channel. I am just one of many channels on Nebula, and you can get exclusive access to originals from my favorite channels, like Mustard's The Origins of Stealth, which details the fascinating history of the F117 Nighthawk, or Wendover Productions' 3-part trivia game show that I took part in. This is simply the best way to support the channels you enjoy while getting something awesome in return. If you are looking for something else to watch right now, there is a playlist to the entire Insane Engineering series on screen now, along with a link to Real Science's latest video about the incredible efforts we are making to program bacteria to take on our most difficult problems.